Alright, in this tutorial, we're going to be looking at the applications of dimensions. In the previous video, we talked about what dimensional analysis is all about and how to find the dimension of a physical quantity. If you've not watched that video, please check for the video in the description and make sure you go through it before coming back to this. So verification of correctness of a physical equation. This is one of the applications of dimension. All right. Remember, we are looking at applications of dimension. Number one here, we have verification of correctness of a physical equation. So you can have an equation like the equations of linear motion. You can have v equals u plus at. You can have something like maybe s equals ut plus half at squared. All right, equations like this, and then you want to verify if these equations are correct. All right, to verify the correctness of these equations, we can make use of dimensional analysis. So we can look at an example here. This one here says a student in an examination is no longer sure of the exact form of one of the equations of motion, s equals ut plus half at squared. How does he remember? All right, so that student in the exam is not sure if this equation s equals ut plus half at squared is correct. All right, so how does he verify that this equation is correct? Now let me say this before we proceed. To prove that an equation is correct, the left hand side, all right, of that equation must be equal to the right hand side. That's what you have on the left hand side must be equal to what you have on the right hand side. If the dimension on the left hand side is not equal to the dimension on the right hand side, then the equation is not correct. I'll take it again. For an equation or for a physical equation to be correct, the dimension on the left hand side must be the same as the dimension on the right hand side. If the dimensions of the left hand side and the right hand side are not the same, then the equation is not correct. So let's find out if this equation s equals ut plus half at squared is correct. All we need to do here is solve for dimension of the left hand side. So say for left hand side, all right, we have s. What's the dimension for s? S stands for displacement, all right, and displacement is a form of length, so the dimension is L. All right, please, if you've not checked the video on dimensional analysis, all right, or how to calculate dimensions, please go check it out. The link is just right there in the description of this video. All right, so now let's proceed. Dimension for displacement is L, so we have S equals L. So that is the only displacement is the only physical quantity we have on the left hand side, so we can just take note of it that the dimension is L. Now for the right hand side, let's see if we can get the dimension of the right hand side. Now the right hand side, we have ut plus half at squared. All right, so let's try to get the dimension on the right hand side and see if the dimension of the right hand side will be the same as the dimension of the left hand side. Now u here is velocity, all right, and velocity is lt minus 1. That's the dimension for velocity, lt minus 1. And then t is time, all right. The dimension for time is capital letter T, so we have times t. All right, so this is ut. The whole of this is ut. They will say plus, remember we're solving for dimension on the right hand side. That's what we have here. We want to get the dimension. All right, so we have plus 1 over 2 times a. A is acceleration and the dimension is lt minus 2 times time squared, so we have t squared. So if we take this further, we're going to have L t raised to power minus 1 times t raised to power 1. This is going to be t raised to power, the power of this is minus 1, the power of this is plus 1. All right, and remember they are multiplying t and t, that's to say the bases are the same, so we'll add the power, so we have minus 1 plus 1. All right, and that will give us lt raised to power minus 1 plus 1 plus 1 over 2 times lt raised to power, we have t here as a base, t here as another base, so we'll add the powers and that will give us minus 2 plus 2. All right, the bases are the same, that's why we can add the powers. All right, and they are multiplying, that's the reason for addition. So that's going to give us lt minus 1 plus 1 is 0. So I have LT raised to power 0 plus 1 over 2 LT raised to power minus 2 plus 2 is also 0. So we have T raised to power 0. At the end of the day, we're going to have this T raised to power 0. Alright, just T is raised to power 0, not LT. Alright, so T raised to power 0 is 1. Any T raised to power 0 is 1. So we're going to have L times 1. That will give us L plus half, all right, times L. All right, so that's going to give us 1L plus half L. That's going to give us 1.5 L. That's 3 over 2L. Okay, so now let's come back. The dimension on the left hand side is L. What's the dimension on the right hand side? It's also L. All right, forget about this number here. It's just a constant. Our focus here is just the dimension. So you see here that the dimension on the left hand side, which is L, is the same as the dimension on the right hand side, okay, which is also L. So in that case, this equation S equals UT plus half AT squared is correct. Now we can also use dimension to derive units of physical quantities. For instance, you can have a question like this. They say, what is the unit of velocity? You can use dimension to determine the unit of velocity. All right, velocity has dimension to be LT minus 1. All right, please make sure you check that video on dimensional analysis. The link to the video is in the description. Okay, so now we have velocity to be LT minus 1. How do we get the unit for velocity? So we have V equals L is length, and length is measured in meters. T is time, dimension for time, and time is measured in seconds. So we have ms raised to power minus 1, which is the same thing as in meters per second, or you can write it this way. So this is the unit for velocity. You can have something maybe like acceleration. Acceleration. Let's say you want to get the unit of acceleration. The dimension for acceleration is LT minus 2. From this, we can get the unit of acceleration. L is in meters, length in meters, T is dimension for time, and time is measured in seconds. So we have ms raised to power minus 2, which is meters per second squared. So this is the dimension, the unit for acceleration. We can also look at force. Force, all right. Force, the dimension for force is mlt raised to power minus 2. Okay, how did we get that? We know that force is mass times acceleration. This was also treated in the previous video on dimensional analysis. Okay, so force is mass times acceleration. So we have mass dimension to be m, acceleration dimension to be lt minus 2. All right, so that's it. So this is the dimension for force. So now if we want to get the unit of force, m is the dimension for mass and is measured in kilogram. L is the dimension for length and is measured in meter. T is the dimension for time and is measured in seconds. All right, so the unit of force is kilogram meter per second squared, though we usually use Newton. All right, Newton is simply the name of a scientist that made so much contribution to what we know as force in modern day. All right, Isaac Newton. Okay, it was named after him. Force, the unit of force was named after him, so that's why most times we use Newton. But the actual unit of force is kilogram meter per second squared. Now the next one here says derivation of the exact relationship between physical quantities. Now this one is very important. We can use dimension, all right, to get the relationship between physical quantities. And let's look at an example here. They said, suppose the period of oscillation t of a simple pendulum depends on the mass m of the period of the pendulum bulb, the length L of the thread, and the acceleration due to gravity g. Use method of dimensions to find the correct relation. Okay, so use dimension to find the correct relation. That's to show the exact relationship. All right, so now I'm going to break it down step by step how we're going to do this. Now they say suppose the period of oscillation t, so we have t, okay, depends on. Now whenever you hear this word depends, as long as you're looking at relationship between physical quantity, we make use of our proportionality sign. All right, so we want to write this whole sentence mathematically. We want to present it in a mathematical form. So we have suppose period of oscillation t of simple pendulum depends. All right, depends. All right, how do we write depends? This is symbol. We use our proportionality sign. So it says suppose the period of oscillation depends on the mass of the pendulum bulb, the length of the thread L, okay, and the acceleration due to gravity G. Use method of dimensions to find the correct relation. So this is not yet the correct relation. All right. To know the correct relation, we are going to assign letters as powers here. We're going to use letters as powers. So the value of those letters is what will tell us the exact relation. In this case, we can use letter A, B, and C. Okay. We're going to assign letters here as powers. So the value of this letter A, B, and C is what will tell us the exact relationship between period, mass, length, and gravity of a simple pendulum. All right, so that is step one. All right, first we write this whole thing mathematically. Period depends on mass, length, and acceleration due to gravity. The next thing is to assign powers, all right, unknown or letters as powers here, and then we'll solve for the value of these letters. All right, so let's go on. Now, this is proportionality sign. In order to be able to solve this thing, we need to convert it to an equation. All right, so we need to change this proportionality sign to equality sign. So how do we go about that? We're going to have t equals, we introduce our constant. Anytime you change proportionality sign to equality sign or equal to, you introduce your constant. So we have t equals k m raised to power a l raised to power b g raised to power c. Okay, so now we can solve our equation. Now, in order to be able to solve this thing correctly, we need to convert all the quantities we have there, all right, all the quantities we have here to their respective dimensions. Okay, so convert them to their respective dimensions, and then we equate dimension on the left hand side with dimension on the right hand side. Now, this is period. Okay, dimension for period is still capital letter T. Okay, period is a form of time, so it has dimension to be t. And then we have equals, k is a constant, it's not dimension, so we can ignore it. We can ignore k here. All right, it does not have any dimension, it's a constant. All right, so we ignore it, it's dimensionless. And then we'll go to mass. Dimension for mass is capital letter M. All right, raised to power a. And then dimension for length is capital letter L raised to power b. Dimension for acceleration due to gravity. Acceleration due to gravity is a form of acceleration. So it will have the same dimension as acceleration, which is LT minus 2. So we are going to have LT minus 2 all raised to power C. All right, this is G, acceleration due to gravity. The whole of this is also G. So it's all raised to power C. All right, so now it's time to equate the dimensions. Dimension on the left hand side with dimension on the right hand side. On the right hand side, you have M, L, and T. What do you have on the left hand side? You have just T. But we can equate, we can introduce M and L in such a way that it's not going to alter what this equation actually stands for. All right. So how do we introduce that? We say M raised to power 0, L raised to power 0. M raised to power 0 is 1, L raised to power 0 is 1. So we have 1 times T, which is still T. So you did not alter this. All right. It's still the same thing. So now we can equate dimension on the left hand side with dimension on the right hand side. But before we do that, we need to simplify this equation. You discover here that on the left hand side you have just M, L, and T. All right. Here you have M, L, L, T. All right. So you have L appearing more than one. So we need to simplify it so that we'll have just one single L on the right hand side, one single M, one single T. The same thing on the left hand side. All right. So now we rewrite our equation. We have M raised to power 0, L raised to power 0, T equals this M raised to power A. All right. So now we use this to open up this bracket, L raised to power B, to open up this bracket. But before we do that, there's a power outside. All right. So we use the power first to multiply the powers inside. Okay. So that will give us L raised to power B. Now the power inside there is 1. So we have 1 times C. Okay, so that will give us L raised to power C. This is under laws of indices. Whenever you have a power outside and a power inside, let's say you have A raised to power X or raised to power Y. To simplify this, we multiply the power inside with the power outside. So we have x times y. That will give us a raised to power xy. Alright, so this will give us a raised to power 1 times c is c. And then we have t raised to power minus 2 times c. That will give us minus 2c. And that will give us m raised to power 0, l raised to power 0, and then we have t equals m raised to power a. Now a raised to power b, a raised to power c, you discover that the bases are the same, all right, and they are multiplying. This times this, still the same thing as writing them together. So since the bases are the same, you take one of the base and then add up the powers. So we have b plus c, and then t raised to power of minus 2c. Okay, so now we can equate dimensions, m and m, l and l, t and t, and then we solve. So say for m, for dimension m, for m, okay, we're going to have m raised to power 0, okay, equals m raised to power a. All right, discover that m is appearing on both sides. Okay, so m and m, since it's appearing on both sides in an equation, they will cancel out. Both of them are bases, so we can cancel them out. So at the end of the day, for m, we're going to have a equals 0. And then we'll go to dimension l. So say for l, all right, we have a raised to power 0 equals a raised to power b plus c. So we have a raised to power 0 equals l raised to power b plus c. All right, so now you discover that l is also appearing on both sides, so we'll cancel them out. Then we have 0 equals b plus c, which is the same thing as saying b plus c equals 0. We need to get the value of these unknowns. At this point, we cannot get b and c because there are two unknowns in one equation, so we'll just label it equation 1 so that we can substitute later and get our answer. Okay, so now we'll go to the next one. For dimension t, we have t raised to power 1, t raised to power minus 2c. So we have t raised to power 1 equals t raised to power of minus 2c. All right, the dimensions are appearing on both sides. We have t here, t here. Okay, so we cancel them out, and then we'll be left with 1 equals minus 2c. So to get c, we divide both sides by minus 2. So we have 1 over minus 2 equals minus 2c all over minus 2. This will cancel this. Then you have c equals plus divided by minus is minus. This is positive 1, right? So you have minus 1 over 2 as the dimension for c. All right. So to get dimension of b, we substitute in equation 1 here. So it says substitute c equals minus half in equation 1. All right, so wherever we see c in equation 1, we'll put minus half. So we have b plus minus half equals 0. Plus minus is minus, so we have b minus half equals 0. So b will be equal to, you move minus half to this other side, it becomes b equals half. All right, so at this point now, we've gotten the powers, the values of a, b, and c. So we can now determine the exact relation. Remember, I told you earlier on that the exact relationship will be determined by these powers, a, b, and c. That's what will tell us the exact relationship. All right. So once you've gotten the mathematical expression of this whole sentence, of this whole thing here, the next thing is to assign letters as unknowns. All right, and then solve for the value of those letters. The value of those letters is what will tell you the exact relationship between the physical quantities. So now I've gotten the value of those letters. So now let's get the exact relationship. From here we have t is dependent on m raised to power a. A is what? 0. So we have m raised to power 0. Okay. L raised to power b. B is what? Half. So we have b raised to power half. And then g raised to power what? C. C is minus half. So we have minus half. Okay. So now this is going to give us t is dependent on m raised to power 0 is 0. Sorry, m raised to power 0 is 1. Alright, so the whole of this will be out because 1 times the whole of this is still the same thing. So we are going to have the period is dependent on the length raised to power half and g raised to power minus half. Okay, Now this negative power, we can take the inverse. All right, g raised power minus half is the same as saying g raised power minus half over 1. From our laws of indices, if you have a negative power, let's say a raised power minus x, if you take the inverse, it becomes 1 over a raised power x. The power becomes positive. All right, so this is now going to become t is dependent on l raised power half, all right, times 1 over g raised power half. Okay, if we simplify this further, we're going to arrive at the period, okay, to be l raised power half times 1. That will give us t raised is dependent on l raised power half over g raised power half. Okay, so this is the exact relationship. And whenever we have half as power, I see the same thing as saying square roots. So this whole thing here, all right, this whole thing here can still be simplified. All right, this final answer here can still be simplified, and then we can write it as t, okay, being the period, is dependent on square root of L over square root of G. Raised power half is still the same as square root. If you have a raised power half, is simply square root of a. All right, x raised power half is square root of x. So this is it. Okay, and this can be simplified to this is root here, so we can say t is dependent on all square root of L over G. Square root of square root of, so take all square root. So this is the exact relationship between them, between L, G, and T. Okay, so you can see that M is out of the equation because M is not important here. All right, so the mass of the pendulum bulb is irrelevant. All right, so here you can see that the period is directly proportional to the square root of length and inversely proportional to the acceleration due to gravity. So that is the answer to this question. Okay, so if this video was of help to you, please make sure to subscribe to our channel and feel free to share this video. All right, like the video, share the video to your friends and to your colleagues, and also tell them about our channel. Very, very important. Okay, and if you have any question, please drop a comment. If this video was also of great help to you, you can also drop it there in the comment section. I will see you in the next video.